Alright, this is part 6 of our lesson on graphing rational functions. And we're picking up here with number 7. Alright, let's actually look at the horizontal asymptote first. There will be a horizontal asymptote if the horizontal asymptote depends on the degree. So remember, if the top degree is lower than the bottom, then it would be y equals 0. If the degrees are equal, then we do leading coefficient divided by leading coefficient. So it would be y equals 1 in this case. But if the top degree is higher than the bottom degree, then there is no horizontal asymptote. So we'll just put none. But maybe there is a slant asymptote. There will be a slant asymptote if the top degree is 1 higher than the bottom. So the numerator is degree 3, the denominator is degree 2, so that is 1 higher. So there will be a slant asymptote for this problem. To find the slant asymptote, I need to do long division and look at the quotient. Okay, so let's do that now. So if I do x squared plus 2x minus 3, and I divide that into the numerator. Okay, and so here we go with the long division. Start off looking at these two and ask yourself, x squared times what will give me x to the third power? Clearly that's x, and I'm going to put it over here in the x column. Now take that and do the distributive property with it. Alright, so x times x squared is x to the third power. X times 2x is 2x squared. X times negative 3 is negative 3x. Okay, subtract by changing the sign. So this will become minus, this will become minus, and this will become plus. So these cancel out. Here I'm going to get negative 3x squared and negative 1x. And then I'll just bring down the plus 4. And then I sort of start over again. Alright, now I'm looking at the x squared and the negative 3x squared. And once again I'm asking myself, x squared times what will make negative 3x squared? Clearly the answer to that question is negative 3. Then I take my negative 3 and I distribute. Alright, negative 3 times x squared is in fact negative 3x squared like we wanted. Negative 3 times 2x is negative 6x. And negative 3 times negative 3 is positive 9. Alright, we will subtract by changing the signs. So this will become positive, this will become positive, and this will be negative. So these cancel out. Here you get 5x and minus 5. Okay, that's my remainder. But as far as the slant asymptote, I don't need to worry about that because the slant asymptote is just going to come from the quotient here. Alright, so this right here, the quotient is going to give me the slant asymptote. Alright, so the slant asymptote is going to be y equals x minus 3. Alright, this is a diagonal line. In fact, let's go ahead and graph this diagonal line right now. Remember y equals mx plus b. This negative 3 is the y-intercept of this line. So this will be the y-intercept of this asymptote. Okay, and then the slope, right, is like 1 over 1. So that means it's going to be up 1, right 1, like this. Okay, so this is going to be my slant asymptote. Alright, you can just continue the pattern. Alright, so there's our slant asymptote. We'll come back to that in a minute. Okay, now let's go back to talking about vertical asymptotes and holes in the graph. To discover the vertical asymptotes and holes, we will need to factor the numerator and the denominator. So let's work on that right now. Okay, factoring the numerator. Let's see if I have room right here. This looks like a grouping situation to me. I see the 4 terms. I always look for grouping. There's a common factor here, x squared. So looking at the first 2 terms, if I pull out x squared, then that's going to leave behind x minus 1. Now looking at the second 2 terms, we have a common factor of negative 4. Got to pull that out. And that's going to leave behind x minus 1. And again, I know it will be x minus 1 because if I did the distributive property right now, negative 4 times x would give me negative 4x. Negative 4 times negative 1 would give me positive 4, which is what I want. Because these factors are the same, x minus 1 and x minus 1, I can factor out that common factor. Alright, I can put the x minus 1 out front. That's going to leave behind x squared minus 4. But then that is the difference of 2 squares. So this will factor as x plus 2 times x minus 2. So completely factored, we have x minus 1 times x plus 2 times x minus 2. So that's the numerator. Alright, x minus 1. Okay, so here we go. So the numerator was x minus 1 times x plus 2 times x minus 2. Now, how about the denominator? Okay, the denominator is x squared plus 2x minus 3. I'm running out of room here, so I'm just going to jump over to another screen. So x squared plus 2x minus 3. Let's go ahead and factor this down. X squared can only factor as x times x. 3 can only factor as 3 times 1. Now you know that inner plus outer must equal the middle. So we're trying to get the middle to be positive 2x. Inner, I have 3x. Outer, I have 1x. In order to get a positive 2 out of this, I need a positive 3 and a negative 1. So there's my positive 3 and there's my negative 1. And that also gives me negative 3 because positive times a negative is a negative. So this is the correct factorization, x plus 3 times x minus 1. Okay, x plus 3 times x minus 1. Now I wrote it this way because I'm looking ahead and I'm seeing what's about to cancel. And these x minus 1s can cancel out. Thus, the x minus 1 in the denominator will not yield a vertical asymptote. Instead, it will deliver a hole in the graph. So if I take this x minus 1 and I set it equal to 0, adding 1 to both sides gives me x equals 1. But this is not a vertical asymptote. This means that there is a hole at 1 comma something. Alright, so let's go ahead and jot that down. So there's a hole at 1 comma something. Now I would really love to know what the y value of the hole is. To find that y value, I need to put this part of the function in my calculator. Or I could just plug in 1 for all these x's. Either way, I'm going to use the calculator though. So x plus 2, x minus 2, x plus 3. Alright, let's table it up. Okay, so we had x plus 2 times x minus 2 over x plus 3. Okay, and we want to know what's happening at an x value of 1. So I'm going to tell it start at 1. Okay, at 1, I'm coming up with negative 3/4. Okay, so negative 3/4. So let's see. So I have a hole at 1, comma, negative 3/4. Alright, so now let's take a look at the vertical asymptote that we get from the x plus 3 that didn't cancel out. So if I set that equal to 0, that gives me x equals negative 3. Okay, and that will be a vertical asymptote. Okay, so I have a vertical asymptote at x equals negative 3. Alright, so I already graphed the slant asymptote here. So now let me graph the vertical asymptote and the hole. Alright, so there's my vertical asymptote at negative 3, and there's the hole at 1, comma, negative 3/4. Okay, now let's use our calculator to find other values. So we'll need some values to the left of the vertical asymptote. We'll need some values in the middle, and we'll need some values over here to the right, you know, like over here at 4, 5, 6, that type of thing. So let's check it out. Let's check it out. Okay, I think it's already in the calculator, so we can just use this. So we want to know what's going on at, well, for example, negative 4. Okay, so let's just start off at negative 4. Alright, at negative 4 we're at negative 12. Wow. So that's really off the chart. Oh, you know what? This is going to be tricky because I think we might have a loop down here in this area that's off the chart. So well, let's just do our best to capture these values, alright? Because this graph is a little tough. But so at negative 4 we're at negative 12. Okay, so this is about negative 11. Negative 12 would be about like here. Okay, what about negative 5? Okay, at negative 5 we're at negative 10.5. Okay, so at negative 5 we're at negative 10 and a half. So that would be like about here. Okay, what about negative 6? Alright, that's negative 10.6. It's almost the same, but like maybe a slight amount lower. Okay, so I sort of see what's happening here. I feel like I should extend this asymptote further. Okay, I feel like I better stretch this out because I think the loop is happening in here. Alright, so let's just do a couple more. So I saw negative 6 at negative 7. What's going on? I'm at negative 11.25. Okay, so at negative 7, you know, I'm about here. So you get the idea. Alright, so what must be happening, okay, considering the asymptotes, it must be doing like this. Alright, notice that all these points are sort of off the graph, but we really need them. So just do your best and just extend. Okay, so that's what's going on over here. Okay, now let's take a look and see what's happening in this area. So let's look at like negative 2, negative 1, 0. So let's look at negative 2. At negative 2 we're at 0. Okay, at negative 1 we're at negative 1.5. So that would be like here. At 0, we're at negative 1.3. Alright, we already see what's happening here at 1. What about at 2? Alright, 2 comma 0 actually. Alright, and you can bet that from there it's going to go on and approach this asymptote. So for example, let's see what else we have. Any whole numbers here coming up? Because that would be fun to see. Nope, no whole numbers. Alright, so I'll just go back and say, for example, where did I leave off? Let's look at 4, for example. Alright, so at 4, we're at 1.7. Okay, so at 4, I'm at 1.7, would be right about here. So clearly it's just going to approach the asymptote after that. Let's go ahead and look at this decimal right here. Okay, I want to know what's happening really close to the asymptote. So I want to look at negative 2.5. Okay, so I'm going to go back to my table. Since I just want this one value, I'll just go ahead and type in negative 2.5 and tell it to start there. Okay, so that's 9 halves. Okay, which is 4.5. Okay, so right here up close, it's at 4.5. So this gives me a nice clear picture of what's going on in here. Alright, we're approaching the asymptote. Okay, like this. It's going to curve around like that. And then it's going to again approach the asymptote. Okay, so that is a nice picture of what this graph is going to look like. Alright, let's go ahead and talk about the domain of this graph. Normally, for the domain, we would just talk about this branch over here and this branch up here. But because of the hole, this upper branch is actually separated into 2 parts. So that means my domain is going to have 3 parts. 1 for the lower branch and 2 for the upper branch. Alright, so first of all, the domain of this lower branch. Remember, we're doing x values, so alright, we're thinking left to right. So this graph goes to negative infinity as we go to the left. But as we go to the right, it stops here at the vertical asymptote, which is negative 3. So, so the domain for this part of the graph is negative infinity to negative 3. So let's go ahead and record that. So we're going to have negative infinity to negative 3 union. Okay, and then we're going to pick up from there with this portion of the graph leading up to the hole. So that's going to be negative 3 to 1. Negative 3 to 1. Okay, because that's just x value. So negative 3 to 1 union. And then we'll pick up from there and we'll go 1 to infinity. Not because it's going up, but infinity because we're going to the right. So 1 to infinity. Alright, 1 to infinity. Now we're going to leave all of these as round parentheses because you can't reach the asymptote and the hole is not included. So the round parentheses are leaving out the asymptote and leaving out the hole. That's at 1. Okay, now remember, a continuous graph is a graph that's unbroken. So this graph is broken in 2 ways. It's got these asymptotes that are splitting it up into parts, and it's got this hole in the graph. Okay, the asymptotes are called infinite discontinuities. The hole is called a point discontinuity. But either way, this is definitely discontinuous. Alright, and again, I changed my mind about how I wanted to format the answer part. So just go with it as best you can if your paper still looks different from mine. But continuous or discontinuous, it's definitely discontinuous because it's broken into parts. Now, the discontinuities are the asymptotes and wholes. Let's label each one of these discontinuities as removable or non-removable. Now, the only removable discontinuity is a hole in the graph, a point discontinuity. So we will label this one as removable. Okay, but the other the asymptotes are non-removable. Okay, and that is it for problem number 7. Okay, problem number 7 had a lot going on, and this video is running long. So that's going to be the end for this video, and we have one more problem left, and this is one of the longest lessons I've ever done. That wasn't a test, especially. Okay, so one more problem. So I'll see you on the next video for problem number 8.